You may be wondering what the graph on the thumbnail is. It's a different kind of simple harmonic motion, where we begin to consider drag in the sense that drag might be some force that is opposite to the velocity and proportional to the velocity. Hello everyone, and welcome to Watch Me Do Math, and in this video we're going to be re-deriving the shape of that graph in the thumbnail and trying to explain in different situations how a body might oscillate if there was a drag force that was proportional to and in the opposite direction of a body's velocity, compared to the idealized and kind of perfect scenario of simple harmonic motion, where we're only considering some restoring force on the body due to its position away from an equilibrium. So while this might look like a perfect sine wave, we want to investigate what the xt graph, or the displacement graph with respect to time, would look like for this kind of motion, whether it would always look like the one I show you on the thumbnail, or whether there are other forms of it to consider as well. Alright, so let's begin. Say we want to find out x in terms of t. It's something that does not seem the most intuitive thing to do, because none of these equations has a term involving time in it. Or do they? If you look at the simple harmonic motion equation, a is minus omega squared x, where x is this displacement away from the equilibrium, we can take a to be the second differential of displacement with respect to time, because you differentiate displacement to get velocity, and you differentiate velocity with respect to time to get acceleration, as velocity is the rate of change of displacement over time, and acceleration is the rate of change of velocity over time. So a is d squared x over dt squared, the second differential of x with respect to time, and we get that the simple harmonic motion equation is actually a differential equation with respect to time, and x, of course, where omega is a constant, that is sort of the angular velocity of the system as it passes through the phases of a sine wave. This concept is covered in more detail in my other videos about simple harmonic motion, so I won't go too in-depth here, because in this video I'm actually going to be focusing more on the math behind this, and an alternate way of deriving the position time graph that does not involve the sort of breaking dA by dt into dA by dx, dx by dt, and so on and so forth. We won't be using any of this. Instead, we will be solving this differential equation, which is a second order differential equation because it involves a second differential, using a technique that is not really taught in IB Maths, but I found it on mathsisfun.com when I was first looking up why the SHM equation of motion looks like the sine, even though there is no sine in the original thing. And the technique they use to solve these differential equations, where you have sort of a constant and the second differential, and a constant in the first differential, and the function. This form of differential equations basically has a specific technique they use to solve it, which relies on the fact that there are some functions that, when differentiated, look very similar to what they were before they were differentiated. And that function is e to the t in its most pure form, because as many times as you differentiate this, it's not going to change. E to the t will always be e to the t. So we want to do something similar. Say we have some differential equation in this form, where there's a constant times the second differential, and a constant times the first differential, and a constant times the function itself. A way that people solve it is by letting that function be some e to the lambda t, where lambda is a factor yet to be discovered. And in that sense, the second differential with respect to time will be lambda e to the lambda t by the chain rule, and the first differential with respect to time will be lambda e lambda t by the chain rule, and the second differential with respect to time will be lambda squared e to the lambda t by the chain rule. So this sort of way of solving a second-order differential equation, or really an n-order differential equation, if you're good enough at factorizing polynomials, which I'm going to explain in a moment, stood out to me as something that was pretty cool and pretty beautiful, because of how simple it actually is. And I even think that this method is simple enough that it ought to be taught in an IB higher level scenario, albeit with some of the edge cases removed, because this does lead you into some pretty crazy territory if you let it go too far. So anyway, suppose that x is this e to the lambda t. This equation then becomes, taking the second differential of x as equal to, or this being the acceleration term, being equal to minus omega squared x. This tells us that lambda squared e to the lambda t equals minus omega squared e to the lambda t. And the cool thing about this, the reason that we use e to the t in the first place, the reason that we use those kinds of functions, is because they are very similar to themselves when they differentiate, to the point that you have a common factor among every single differential, namely the e to the lambda t that you started with. So in this equation, we can cancel out e to the lambda t and find something in terms of lambda. So we get lambda squared equals minus omega squared. Right, so how does this work? Well, firstly, we know that omega is greater than 0. It's an angular velocity. It's an angular speed, pretty much. And omega squared is definitely going to be 0, because omega in a real physical scenario is always going to be a real number. So if omega squared is greater than 0, that means lambda squared must be less than 0, or less than or equal to 0. Let's suppose that omega is not 0, otherwise there would be no motion. So if lambda squared is less than or equal to 0, then taking the square root of it would lead us to the conclusion that lambda is an imaginary number. And what is the imaginary part of lambda then? Well, if lambda squared is minus omega squared, then lambda would be taking the square root of minus omega squared, factorizing the square root into the root of minus 1 multiplied by the root of the positive omega squared. Lambda would be plus or minus omega I. So substituting that back into our original expression, hopefully if you've watched my other video on simple harmonic motion and how we get the xt is sine omega t, or x0 sine omega t. If you've watched my other video on how we get this, I hope that you can appreciate this method, if you are someone who has done the relevant math, as something that is so much faster for getting that same conclusion. Because if we substitute this lambda back into the e to the lambda t expression that we thought x was going to be, then we get xt is e to the plus or minus I omega t. So here we have a complex number, because complex numbers usually take the form e to the I theta, or r e to the I theta. And in this case, we interpret r as being x0. I know that I haven't done this method its mathematically rigorous justice, but I'm just going to tell you that x0 is basically what we get out of this. If xt is e to the plus or minus I omega t, then we get xt being equal to cis, or cos plus I sine theta, where in this case theta is omega t, or cos omega t plus I sine omega t. And remember that there is a plus or minus in here. So this cosine plus or minus omega t can just be interpreted as cosine omega t because cosine is an even function. I think it's even. Well, anyway, I mean to say that it is symmetrical around the y-axis, so whether you give it a positive k or a negative k, the output's going to be the same. So cos plus or minus omega t is just going to be cos omega t, and that plus or minus takes care of itself. And in the meantime, you have this sine plus or minus omega t, which, because sine is an odd function, i.e. it is sort of rotationally symmetric around 0, 0, and so if you have a x here leading you to a positive y here, then the negative x will lead you to that negative y here, meaning that sine plus or minus omega t is plus or minus sine omega t, leading us to the conclusion that xt is cos omega t plus or minus I sine omega t. Now here's the thing. Remove this consideration from your head because it was inaccurate. I meant to say that it was x naught cos omega t because you start at a maximum or a minimum when you let go of a body to begin this kind of simple harmonic motion without a drag force. If the position of the body at a particular time is a complex number, how do we interpret this in real life? So I've had a lot of thought about this because I know that our final result is going to be the x naught cos omega t. However, in thinking about this, I have not really been able to find any particular reason why we discard the imaginary term here, except for the fact that it doesn't actually involve any real motion. So I think the logic in the, if I'm not mistaken, the logic in the physics sense is that you take the real part of xt to be your xt, because the imaginary part does not describe any real motion. But I'm not entirely sure on this, and if anyone does know, I would be delighted to find out, because the resources I read in preparation for making this video did not make that really clear. So anyway, that's how we get the x naught cos omega t expression for the simple harmonic motion position time graph, i.e. something that looks like this. And now I want to take this to the next level by bringing in that drag term. So, given that we've had all of this progress so far, let's move over to the side and start working with a drag force. So we're going to use the same method of solving the differential equation in order to investigate the system that has a drag force. And like I said, that method of using e to the lambda t as your sort of function that you're going to deal with in a differential equation because it is similar to itself shines really well in this particular form of differential equation because you have to deal with both the function itself, the first differential, and the second differential. So x equals, i.e. you have to deal with x double prime, x prime, and x t. And when you are dealing with something that is in the form of e to the lambda t, these will all be some multiple of e to the lambda t, as the chain rule implies when you differentiate it a certain number of times. So, going back to the equation that we had at the beginning, where k is the constant of proportionality for the acceleration due to drag that is caused by its velocity being at a certain level in the opposite direction of its velocity, we get the equation of motion x double prime, or the second differential of x with respect to time, acceleration, is dependent on this restoring force, which is the usual characteristic of simple harmonic motion, and some drag force, where this drag force is relevant basically to how the motion of the oscillating thing decays over time. By the way, if I say bottle instead of body at any point in this video, it's because this video is a spin-off of some work I did for my physics IA. I didn't use this much math in it, but I liked the situation of the bottle, and I did investigate that for my written work. And it was pretty interesting, and I don't know if I do it again, but it was pretty interesting, and that's why I wanted to share this with you guys. So x double prime is minus omega squared x minus k x dash, and just remember that this equation, even though it's a differential equation, it still represents the relationship between three real-life quantities, i.e. the acceleration on the bottle is dependent firstly on the distance away the bottle is from the equilibrium position, as well as the current speed of the bottle. So, going back to this differential equation form, we get lambda squared e to the lambda t minus is equal to minus omega squared, not lambda, minus omega squared e to the lambda t minus k lambda e to the lambda t. And again, with this technique, the beauty of it is that you have this e to the lambda t term, which cancels out across all of the differentials or functions that it appears in. So this cancels out to 1 if we divide by e to the lambda t on both sides, and we get lambda squared is minus omega squared minus k lambda. Or, in other words, we get a quadratic equation that we need to solve in terms of lambda, where lambda squared plus k lambda plus omega squared is equal to 0. So how do we go about this? Well, in order to best illustrate the point I'm going to make about the different scenarios that we might find out depending on the sizes of k and omega squared, we will have to look at different solutions, whether they are imaginary or real. I mean complex or real. So I'm going to solve this by completing the square rather than through the traditional quadratic formula method, because I want you to see it like unfold before you rather than plug it into a formula and elucidate that the whole thing is possibly a complex number, or lambda is possibly a complex number, which leads us back to the sine stuff that we were messing around with earlier. So lambda squared plus k lambda plus omega squared is 0. If we complete the square, lambda plus k over 2 squared minus k squared over 4 plus omega squared must be equal to 0, because knowing that the coefficient of the single lambda term is k tells us that we can use the square, the fact that lambda plus k over 2 squared is going to be lambda squared plus k lambda plus k squared over 4, and then subtract the k squared over 4 on the outside to make sure that we haven't actually changed anything in the expression, to get this lambda plus k over 2 squared equals adding k squared over 4 to both sides and subtracting omega squared from both sides equals k squared over 4 minus omega squared. And then taking the square root of both sides, lambda plus k over 2 is equal to plus or minus the square root of this thing, plus or minus the square root of k squared over 4 minus omega squared. And, of course, subtract k over 2 from both sides to get our final answer. Okay, so now we've got to consider the different outcomes based on the value of this determinant, which I'm going to call delta. From your knowledge of quadratic equations, if you're watching this video and understood everything so far, you probably do have a lot of knowledge on these equations. If this delta, which we're going to call which is usually called the discriminant, is positive, then lambda is real. And what does that imply for our x to the t function? That means that x to the t is going to be some function e to the lambda t without any imaginary part. So e to the minus k over 2 plus or minus the square root of k squared over 4 minus omega squared will be, if we investigate this scenario further, e to the minus k over 2 either multiplied by e to the root k squared over 4 minus omega squared, or e to the k over 2 divided by this thing. Now, how do we deal with that? So, say we, instead of calling this delta, we call this delta squared, the discriminant squared, so that it's more convenient for us to deal with the system of equations. If delta squared was greater than 0 and lambda was real, then we'd get our two functions in the form x in terms of t is e to the minus k over 2. Oh, and this whole thing must be multiplied by t, of course. I really forgot that. Minus k over 2t times or divided by e to the delta. Now the thing is, this e to the delta seems like we need to consider that it is a constant term. So in actual fact, I think it doesn't really matter which solution you take, plus or minus, because either way you will get a similar looking graph, e to the minus positive number t, looking like this, or like this, depending on what x0 is, whether it's positive or negative. So this is what happens when delta squared is greater than 0. And I'm not too sure on the terminology, but I'm fairly certain that this kind of motion is called overdamped motion, because the thing that's meant to be oscillating doesn't actually oscillate at all. It sort of oscillates, it tries to oscillate once, then peters out. So that's the first type of solution that we can interpret from the graph. And then suppose delta squared were equal to 0, Actually, just going back to the previous example, I found an error in my working. We have this t here, but it's an exponent. And because this whole thing is multiplied by t, this must also be multiplied by t. I found out through some online research, I paused the recording and looked it up just to make sure that I was doing this correctly, that people take the multiplied by e to the delta over the divided by. Because in a real physical situation, if the amount of drag, basically, if this term is greater, because k is greater, that means there is more drag. This omega will not necessarily be greater through any means dependent on drag, so we leave it out of the system. We leave it out of our consideration. But because k is the one that rises when there is more drag, and more drag means that the system should take a longer time to settle down, or the longer time to fall to equilibrium, just like a rock falling through water will take less time to reach an equilibrium than a... Well, that's kind of a bad example, but if you imagine trying to bounce something buoyant in a pool of water versus bouncing something buoyant in a pool of honey, you realize that the one in the honey doesn't bounce so much, as in it's not really it's not free to oscillate as much, and if it's more damped, then it's going to take more time for E to get to lower and lower values, which means that this sort of horizontal stretch factor with respect to time ought to be greater, this negative thing that is multiplied by t. So in reality, xt should be written as e to the minus k over 2 plus discriminant t, plus root of discriminant t. So moving on to the discriminant is 0 situation, we still find that lambda is a real number, but instead this time it's exactly minus k over 2. And the reason I want to consider this as pretty cool is because this actually has a use in some designs. Like, through my research, I found that, for instance, car manufacturers want to make their sort of oscillation or crumpling when a car crashes into a thing, or it may be applied in a different way. Not crashing. It's not crashing. It's shock absorbers. The springs that make your ride feel comfortable in a car want to be critically damped because they want to stop the oscillation as fast as possible. And when I say critically damped, I mean this determinant equals 0 because it's the lowest that you can have this horizontal stretch factor in the equation. It's the lowest you can have this factor such that you will find that oh god, it's not plus delta, is it? It's minus delta, because 1 over k over 2 plus delta will be smaller than 1 over k over 2. Wait, I'm really confusing myself with this. Okay, we're just going to go with it being plus delta for the time being until I can circle back and figure that one out properly. So essentially, when a system has this delta being equal to 0, people call it critically damped because it will approach equilibrium, stay at equilibrium, and not overshoot or oscillate as fast as it possibly can. Right, so going back to this, I really need to think through this, talk through this rigorously. Okay, so if you have e to the bigger number t, then as t goes 0, 1, 2, or e to the minus bigger number t, it would be like 1 over e squared, 1 over e to the 4, 1 over e to the 6. If you have e to the minus smaller number, t, then over time you might have 1 over e to the 0.5, 1 over e to the 1.0, 1 over e to the 1.5. Alright, so this one goes down slower, so it must be having a smaller thing inside the bracket. So we have a minus sign here, removing the plus sign here to make the magnitude of the thing that is multiplied by time smaller. Okay, it's plus discriminant. Good God. Okay. Lambda is minus k over 2 in the critically damped situation where it goes to 0 as fast as it can without overshooting. And the most interesting part of this is when lambda squared is less than 0, because again you'll have that e to the what's it called? E to the minus k over 2 plus delta I t, which is e to the minus k over 2t multiplied by e to the minus I delta t where this becomes cos plus I sine, so sort of cos delta times t plus I sine delta times t, where we ignore the imaginary part of it because we consider imaginary motion non-existent, and then we get e to the minus k over 2 t times cos delta times t. And this is in fact where the graph in the thumbnail of this video comes from, because you have, on the one hand, you have this cos function, which is going to oscillate between -1 and 1. And so if it's multiplied by anything, it means that the whole function is going to oscillate between e to the minus k over 2t and minus e to the minus k over 2t. So in a sense, it's like the e to the minus k over 2t is an envelope for the function to oscillate within, hence the dashed lines when I drew it on the thumbnail of the graph. And it's this special property of the cos function, the fact that it's always between -1 and 1, that allows us to say it's an envelope, because, as I mentioned earlier, the maximum and minimum things it's oscillating between are basically, it is the amplitude that decays with time, which is why we get this sort of graph in the first place, because this dashed line will be your e to the minus k over 2 and e to the minus k over 2t, and inside it's going to oscillate between -1 and 1, just as a cosine function would with an angular speed delta. Alright, so I apologize for the sort of pseudo train wreck that happened at the end of this video, but it's something that is more difficult, more involved than most of the content that I've posted on my channel before. But I hope to share this with you guys because it is really quite interesting. And it uses a lot of mathematical techniques that you don't get to see a lot of the time in physics in order to deal with these situations that are more close to real life, involving forces like drag, even though that drag force proportional to velocity is kind of fictional in the sense that most drag forces are not proportional to velocity of a body. So, knowing all this, I think it's time to end the video here. And if you have any questions on this, I am happy to answer them at watchmedomath@gmail.com. That's watchmedomath@gmail.com. And Until next time, thank you for watching. I'll leave a link to some useful reading in the description in case you want to find out more about this topic, and I'll see you next time.